Hey everyone, welcome to a new chapter. We are in chapter 14. This is Professor Monty, and what we're going to do today, we're going to do sections 14.1 and 14.2. So 14.1, you see it says linear equations with one independent variable. The big question in this chapter is, let's state it this way. Can we predict y if we know x? That's the big question. So we're going to be talking about these specifically in this chapter. We're just talking about linear equations. So if x affects y in some linear fashion, then the answer to this question is going to be yes. If it doesn't, the answer is going to be no. So, but let's start off. We have linear equations. So think about, well, where'd all that go? We have linear equations. Think back to what we did in algebra. We would say y equals mx plus b. Well, what we're doing in statistics, it's that same equation of a line. We change the order of it a little bit. So we essentially do y equals b plus mx, which is kind of weird. But then to go even further, what they're going to do is they're going to say y equals b sub 0 plus b sub 1x. And as before, this b sub 0, the same as the b before, is the y-intercept. And the number multiplied by the x, the b sub 1, is our slope. So we'll say this was b sub 0. We'll say this was b sub 1. And so we've got our y-intercept and our slope. They just put it in a little different format, but it's the same linear equation we did before. Okay, further along with this, we're trying to predict y if we know x. X is called the independent variable. Independent variable. This is the one that can change. We can change this one. That's why it's independent. The y variable is dependent. And we say it's dependent because its value depends on what the x value is. Y depends on the x value. Let me just show you real quickly what we're talking about there. So say we've got an equation, we'll put it in the form that we're talking about. So for example, how about y equals 3 plus 2x? Notice that's in that form, y equals b sub 0 plus b sub 1x. Now, if we think about some values, x and y, this is the same thing we did in algebra. We're going to pick the x values, but we're going to calculate the y values. So let's give a couple values for x. Maybe x is 0. Well, then y, we have to plug it into the formula. Y is going to be 3 plus 2 times 0, which is, of course, 3 plus 0, which is just 3. So that y of 3 depended on the x of 0. When we picked x to be 0, y was dependent on that 0. It became a 3. If we pick x to be 1, now I've got y equals 3 plus 2 times 1. Well, 2 times 1 is 2, plus 3 is 5. So again, y depended on what x was. So we've got points. If we listed these as points, we could certainly graph these. Remember, the x-axis is always horizontal. Y value is always, that axis is always vertical. And so if I do say 0, 3, I start at x is 0, I go up 3, there's 0, 3. And then I have 1, 5, so I go out 1, but I go up 5, 4, 5. So I've got a point 0, 3. I've also got a point 1, 5. So there's my 1, 5 point. This was my 0, 3 point. And then I can draw the line through there. We'll actually change colors so we don't get it confused with the X and Y axes, but there's my graph. And notice it's a linear function, meaning the graph is a line. Okay, so that's what we mean by linear functions. All right, so X is the independent variable, Y is the dependent variable. We know what the equation form looks like, so we can use that. We've actually even seen how to find some values of Y once we pick X. And the line, the blue line that I drew, didn't matter what values of X I picked. If I calculate Y, the point that I get from there will be on that line. That is a line of all the points that satisfy that equation. Y equals 3 plus 2X. Okay, so from there, let's go on. Let's do one of these problems and we'll talk about it. Now let's mention this real quick. In this problem that we had, so remember we had Y equals 3 plus 2X. Remember that 3 is the y-intercept. And what it means is over here, if we look back at this graph, it intercepts or crosses the y-axis when y is 3. The 2 was the slope. We'll say slope equals 2. And what that essentially means, from any point on the curve, if I go up 2 and write 1, I'm going to be another point on the curve. And so that's the idea of the slope. Remember, that's just a quick review of some algebra topics you've probably seen in multiple classes. To get to this class, you should have at least seen some algebra, but maybe not too much, so we'll review it. Okay, so let's go ahead and do a problem. I pulled a problem actually out of the book. Let's see if we can just paste it in or if I have to go find the problem. How about that? There's our problem. So it was problem 1424, air conditioning repairs it's called. And we'll just read it real quickly. Richard's Heating and Cooling in Prescott, Arizona charges $55 an hour plus a $30 service charge. Let X denote the number of hours required for a job and let Y denote the total cost to the customer. Find the equation that expresses Y in terms of X. So for part A, we'll change that back to a black pen. For part A, we're trying to find the equation. Find equation. Well, what we're doing here, they already said X equals number of hours, Y equals total charge. All right, so we're trying to find this. So I want a formula for the total charge. And remember what they told us, it was a $30 service charge. So they're charging us $30 right off the bat to be there. Plus, they also charge us $55 per hour. Now, it might not just be 55 one times they charge us. They would charge us 55 one time if they were there for 1 hour. But if there were 2 hours, we'd have to multiply the 55 times 2. There for 3 hours times 3, etc. Well, we don't know how many hours they're going to be there. We called it X, so it's 55X. So if X was, say, 2 hours, it'd be 30 plus 55 times 2. The 30 doesn't change. It's just the fixed cost. It's the service charge for showing up. But it's just $30 no matter how long they're there. But the $55 is every hour they're there, so we have to multiply that by 55. And that's actually the answer to part A. So then B says determine B sub 0 and B sub 1. Well, remember, we have Y equals B sub 0 plus B sub 1 X. The B sub 1 is always the one multiplied by the X. So in this case, it's the 55. So in this case, B sub 0 is 30. B sub 1 is 55. If they write it in another order, so even if they had written the problem as Y equals 55X plus 30, which would be a fine way to write it, the 55 is still B sub 1 because it's still the number multiplied by the X. It's still the slope. All right, I'm going to erase that so that we don't get confused and say, hey, how come that's written differently there? Okay. So I found B sub 0 and B sub 1, and it says construct a table for the X values and they give us some X values. So this is what I did on that previous problem. So they're going to do X, which is the number of hours, and Y, which is the charge. But remember, we have a formula for that. It's 30 plus 55X. And that's why we say Y is dependent, because its value is going to depend on what X is. Erase that plus 55X, clean that up a little bit. Plus 55X. Okay, and they say specifically use the values of X 0.5, 1, and 2.25. And in all the cases, we're just going to plug it in. So for instance, Y equals 30 plus 55 times 0.5. And so I just plug that into my calculator. I've got a calculator off screen. So let's just say 30 plus 55 times 0.5. And I get 57.5. Well, that's the amount of the charge. If they're there for a half hour, it's still going to cost me $57.50. Since that's money, I'll put it to the nearest penny. If they're there for 1 hour, we do the same thing. We plug 1 in the same way. I'm not going to show this for the 2.25. We'll just plug it in. So I guess I will show it. So both of these we do the same way. Well, that one I can do in my head, that's just $85. The 30 plus 55 times 2.25, I get $153.75. So let's see, this one was $85, this one was $153.75. And so there's my table. So let's see, the table would essentially just be this. I wrote the formula for Y, but it's just the X and Y that we're looking for. Okay. Part D says graph the line that goes through there. Notice when I graph this line, let's see, we'll graph it over here, I think. So part D, you want to slide that over. But part D, graph. But notice what I'm going to do is I'm really only putting quadrant 1. Remember, X was the number of hours. Negative hours don't make any sense, so the stuff to the left doesn't help us. Y can't be negative money charged, so we don't have anything below the x-axis. So we just have this top right region, and so we're going to put some stuff there. Notice the x only goes up to 225, so let's go 1, 2, 3. So this is going to be my hours. Remember, that's x. And y is going to be the total charge. This is going to be money. So let's see. We go up to a little bit above 150. So what, I'm going to go 50, 100, 150. Notice the scales don't have to be the same for x and y. And since I had kind of a short y, that's why we made those so small. But at 0.5 an hour, so halfway, I'm at 57.5. So a little bit above 50. Let's move that up a little bit. At 1 hour, I'm at $85. So maybe about here. Definitely below 100. That didn't look necessarily below 100. I may have to move that. At 2.25, so 2 1/4, I'm up at 153.75. So I'm up above 150, maybe about here. And notice this line connects all these places. Now remember, the y-intercept was 30. If I had a dot right there at 30, that's where I would start. And the line goes something like this. That's going to be the graph of the total charge for coming in to fix the air conditioner. Okay, and look to see what we were fixing. So that's the idea. But any point on that line represents a combination of how many hours the repair person was there and how much the charge was. So for instance, assuming that's a pretty good picture, the next part of this problem actually says on E, apply the graph from D to visually estimate the cost of a job that's 1.75 hours, then calculate it exactly using the formula. So E, cost of job, 1.75 hours. So we're going to say cost is approximately, let's use the graph. So what we do is we go to 1.75, so about here. We go up to the graph, straight up, that's not very straight, straight as I can, and then straight over this way. And we estimate what it was. If our graph's any good, it's probably around 120. Let's say 120, that'll be my guess. Approximately 120, but we can find out exactly what it is. Notice I put squiggly lines for approximately, but the cost is exactly what we go back to the formula, 30 plus 55x. And we know x, it's 30 plus 55 times 1.75. Now I can calculate it exactly, and we'll see how good our picture was. 30 plus 55 times 1.75. And I get 126.25, so I wasn't off by too much. $126.25. I guessed about 120. I was off by $6.25. Not too shabby. Okay, so anyway, that's the idea. That's what we're doing using lines. And again, so remember how we started this. We're trying to use X to predict Y. In this case, if I know X, it predicts what Y is, exactly what Y is, because I have a formula for it. And so going into the next section, we're going to say, well, what if it's not, what if the points don't fall all exactly on a line? What can I do? So let's jump there. That's section 14.2, and we'll talk about what we do. Okay, so let me do this. We'll go back here. We're going to go into 14.2. 14.2, notice it's called the regression equation. So what we're doing here, if points are not all exactly on a line, can we find a line to predict Y? For a given X? Again, that's my question. That's what we're trying to do. Well, here's what we do. We start off, we're going to plot the points. So for instance, suppose we're going to say plot points. So if we have a bunch of XY values, and I'll show you how to do this in a minute, plot points, we're going to make what they call a scatter plot. And so let's say we plot some points. Let's say, again, we have something like this, and we just have a bunch of points here. And they look something like that. And notice they definitely don't all fall on a line, but you can tell that it looks like as X gets bigger, it looks like if there's a line, it's kind of going up. So if X is getting bigger, it looks like Y is getting bigger. In fact, we might be able to put a line in that looks something like this. And that line fairly well predicts all those values. Obviously, it doesn't predict them exactly, but we're going to test to see, hey, does that line, and that line is what we're going to find. This is what we call the regression equation. All the black dots. Okay, so here's the idea. How do we find that regression equation? Let me give you a little bit of theory behind it. Here's what they do. The regression equation, let me even say this. They're going to call it Y, but since it's a prediction Y, they're going to use Y hat because it comes from the sample values. So up here, we'll put that over here. The regression equation is always just And just like p hat, we call that y hat. So the regression equation, y hat, is found, now how about this, using the method of least squares. Sorry about that, got a little excited. And what are they talking about? Method of least squares. Here's the method of least squares. They're going to do this. They're going to get all of these points. And let's use this green one. And they're going to say, you know what? This first point didn't really fall on the line. How far was that away? And what this is, it's the error in prediction. So sometimes they'll just refer to it E. It's also called the residual. And what they do, that's the actual Y value. And so the residual, the point itself is the actual Y value. The point on the line is the predicted value. So the residual is Y minus Y hat. So the actual value minus the predicted. Notice in this case, the Y value is above it. So when I do Y minus Y hat, I'm going to get a positive number. A positive number, a positive residual or a positive error will say, hey, the point was actually above the line. A negative would say it's below the line. So for instance, this one's going to have a negative residual. And so what they do is they take all of these errors and what they want to do is they want to add them up to see how much error there is. The problem is the ones below the line, the points below the line have negative errors. The points above the line have positive errors. And what's going to happen, we're going to get a line that exactly the errors cancel each other out. All the positives cancel out all the negatives and you get 0. So we're going to do what we did with standard deviation to find the minimum error. The method of least squares, what we're going to do is this residual, let's change that to black. The residual, again, which is the error, is, and let's write it Y minus Y hat. So there's my residual. So what they're going to do is we don't want those to cancel out. We do want to add them up. So we're adding up. Remember, sigma means we're going to add up all of these Y minus Y hat. Again, if we add them up as they are, we're going to find lines where the residual, all those cancel each other out and we get 0. So what we're going to do is we're going to square them all so they're all positive. And this is what we mean by the method of least squares. What's squared? Oh, we square the errors and add them up. Whichever of the possible regression lines. So we find any regression line that when I add up all the errors above and below, they cancel each other out. So they'd have a sum of residual of 0. We're going to take all those, square the errors so that they're all positive, and see which one's the smallest. The one with the smallest error becomes the residual line. So let's see. Let's say, state it this way. The line with smallest sum of squared errors. Oops, not squares. Squared errors becomes the residual line. The residual line, the regression line. Sorry about that. All right. And so that's what we do. We find those. And I'll show you an example of that. Okay. Let me state a couple things about regression lines, and then I'll show you a couple problems that we'll do. Here's another example. Say I've got a bunch of points. And again, if I draw a line through there, the line, this time it's going down, it might look something like this. But say I had another point way over here. Well, that number isn't close to the other dots. This is what we would call an outlier. So it's a point far away from rest of the points. We'll put equals right there. Now, if that point, and this one would, if that point would change the regression line considerably, we also call it an influential observation. So this would be a point that if we removed, would change the regression equation considerably. Considerably. So that point that we had there would be an outlier and an influential observation. Notice we may have another point. So see where I've got my line drawn? If I draw another point way, say up here, that point's not close to the other points. That could be an outlier. It's not an influential observation because if I included it, I'd still get that blue line. I would just extend it out further. So it wouldn't change the regression equation, although it is far away from the other points. So you can have an outlier that's not an influential observation, but if it's going to be an influential observation, it does have to be an outlier. I can't imagine where we wouldn't have one of those. So anyway, let's erase that dot. We don't want that. Okay, so that's the idea. But let's go ahead, and what I'm going to do rather than copy and pasting some problems in here, let's go into MyStatLab, since that's where you're going to be doing problems in your homework and the test. And let me show you how to do some of these actually in MyStatLab. Okay, so let's do this. So let's jump, so let's go MyStatLab right here. Let me find it. Homework and exams, there we go. Hopefully it hasn't logged me out. So let's go into chapter 14. See if it didn't log me out. Well, that's good. Okay, the first problem I want to do is problem 12. So let's take a look at this. All right, let that come up. Okay, so this one, graph the linear equation. So they give us two different equations here, lines A and line B. And we have some points, some X and Y points. So those points they've plotted in green. And then they've drawn the two lines. We have to figure out which of these lines is correct. So let's just do a quick sketch to see what's happening. So if I do this, let's see, I'm going to have to use this, aren't I? All right, we should be good. So let's look at that first line. So this will be line A, and it's y equals -1 plus 3x. And let's find some points. Now, we only need 2 points to determine the line. And since they're going from 1 to 3, let's just use 1 and 3. Now, I'm plugging that in for the x. So remember, this is -1 plus 3x. So if I plug in 1 there for the x, I get 3 times 1 is 1. -1 plus 3 is 2. Well, if I plug in 3, 3 times 3 is 9, plus 1 is 10. So now if I graph this, we'll just graph it here. Let's see, notice they have all pretty much quadrant 1. We'll do the same thing. So I'm going to go 1, 2, 3. Let's call this 5 and 10 since I didn't leave myself a little room. Here, let's do this. I'm going to change those because notice on theirs, they do a 10 by 10 grid. Let's do the same grid they do. So it's going to look the same. All right. So we'll go 5, 10, 5, 10. Okay. So I know on that first line, I have 1, 2. So if I have 1's about here, 2's about there, I'm going to have a dot about here. And then 3, 10, it's going to be like that. So the line's going to look something like this. Let's see. It has to go through -1. That's my y-intercept. So the line looks something like this. There's line A. Line B, I can do something similar. Y equals 1 plus 2x. Then I'll go x and y equals 1 plus 2x. I plug in my values. I'll plug the same ones in, 1 and 3. If I plug in 1, 2 times 1 is 2, plus 1 is 3. 2 times 3 is 6, plus 1 is 7. So let's see. Let's use a different color here. We'll use red. Oh, they used red for one of theirs. So I'm going to say, okay, I've got 1, 3. Notice that one was 1, 2, so it's a little bit above. And then 3, 7. Now the 3, 7 was below their 3, 10, so about here. So this line looks like this. And then if I plot these 3 points here, let's plot those in another color. Let's use blue. Oh, they use green. We'll try green. Looks like that green. So let's see. We've got 1, 4. That's going to be a little bit above. 2, 3. And 3, 8. So let's see. That to me looks like D. My colors are off, but this black line is that red dotted line. The red line is their blue line. And then I've got these points. This point should have been, I guess, a little bit up here, a little bit above, which is reasonable. Can I, oh, erase the wrong one. So anyway, I'm going with D. And so we're going to say, I guess all we have to do is tap it. D. Check answer. All right. So we got that one right. So we know what the graph looks like. Let's go on to the next part. So now what they're saying is they're saying, remember when I talked about the method of least squares and we pick the line that has the smallest squared errors? That's what this problem's all about. So they're trying to find this for us. So let's clear those drawings. So we've got the line y equals -1 plus 3x. And it says, okay, when x is 1, the y value was 4. That was the actual y value. This line, y equals, what they should do is they should put a little hat right here, because what this is going to be, this is going to be my predicted y value. So that's the y hat that I'm going to plug in there. And so if I do x and y hat, and again, it's -1 plus 3x. So I'm going to plug it in there. They're doing 1, 2, and 3. And we've already done some of these. We're just plugging it in. So if I plug in 1, I get 3 minus 1 is 2. Plug in 2, I get 6 minus 1 is 5. And 3 is 9 minus 1, 8. That's what's going to go in here. I'm going to plug in 2, 5, 8. I'm not going to draw it in the box because I'll put it in the box when I am able to do it. But now the error, remember the error, oops, that's not an E. The error, that's my residual. That's going to be y minus y hat. So I just subtract these two numbers. This first number, for instance, just think minus here. 4 minus 2 is 2. 3 minus 5 is -2. 8 minus 8 is 0. And notice that's what I was saying. The sum of the errors are going to be 0. They're going to have to cancel each other out. But what about the error squared? So this 2 squared is 4. -2 squared is also 4. and 0 squared is 0. Okay, so this was 2 squared, negative 2 squared, 0 squared. If I add these up, that's my sum of the errors squared, which is what I talked about before. That's my sum of y minus y hat squared. Well, that 4 plus 4 plus 0, I get 8. And so that's going to be the table. Let's plug in all those numbers, see what we get. And if you didn't follow that, we're going to do another table for the other equation to see what we have. But let's see. In case that disappears, let me write these. I had 2, 5, and 8. I had 2, negative 2, 0, and I had 4, 4, 0. Okay, so let's see what happens when I pull this up. So I need to enter these values. I'm going to do that one first. So, oh, you know what'll be easier? Let me flip my computer real quickly so that I have access to all these. And I didn't even have to write those down. Oh, they moved already. So I had, let's see, 2, tab. The error was 2, and the error squared was 4. Tab. The next one was 5. The error was negative 2, and the error squared was 4. The predicted value was 8. The error was 0, and so the error squared was 0. And now we can check our answer. Hey, we got it all right. All right, so let's do the same thing for this next one. Let me clear all the drawings. So we have a different formula here. Now we're using our formula y equals 1 plus 2x. Okay, so our predicted value, again, this is for my prediction. So when I plug in 1, so this value right here is going to be y hat equals 1 plus 2 times 1, because I'm plugging in 1 for x. Well, that's 2 plus 1 is 3. So that's going to be a 3. The error 4 minus 3 is 1. The error squared is also 1, because that's 1 squared. The next number, I'm going to plug in 2 for x. So 2 times 2 is 4, plus 1 is 5. 3 minus 5 is negative 2. And that squared is 4. For the next one, I plug in 3. 2 times 3 is 6, plus 1 is 7. 8 minus 7 is 1. Notice those add up to 0. It's not a very good equals, is it? Let's clean that up a little bit. So that's equal to 0. If I add these up, let's see, that was 1, so 1 squared is 1. But if I add these up, I get 6. So that's what I get. That's my errors squared. This was the sum of my errors. This was the sum of my errors squared. 6. And it's less than the 8 from above, so this is a better prediction. So this was less than 8, so it's the better predictor. In other words, if these are my only 2 choices, this second line is going to be the regression line. Okay, so let's go ahead and put those in. Let me list these up here. Let's see. So at 3, 5, 7, 1, negative 2, 1, 1, 4, 1. In case that moves when I flip my screen again. So let's see. So let me go in here. Am I in there? Yeah. So I'm going to go 3, 1, 1. My next line was 5, negative 2, 4, and then 7, 1, 1. And we'll check that. And winner, I like it. Clear all those things out. And then notice with this problem, it says, hey, which one's the better fit? Which one's the line? Which one's the better line? So let's see. So we would say B had the smaller sum of errors, so B is the better fit. So line B is the better fit because it has the smaller, not sum of errors. They both, the sum of errors, that would have been this column right here. That's the sum of the errors. That's not what we look at. It's this one, the sum of the squared errors, that was the important one. So line B is the better fit because it has the smaller sum of squared errors. So the answer to this one is B. And we check our answer, and of course we get it correct. Fantastic. Okay. So that's how you do those. That's the regression line. That's how we find the minimum errors. All right. So that's a big part of this section. But the next part is actually, how do we find the regression equation? How do we draw this picture? And so what I'm going to do is I'm going to do it two ways. I'm going to show you how to do it on MyStatLab, which works really well if you have access to the computer, which you will. If you don't have access to it, I'll also show you how to do it on the calculator. So let me show you both. And you don't need both. Now I will tell you, if you have access to MyStatLab and they give you a big data set, that's better than having to put in all the data yourself. But let's do one of these. And I hope, well, we'll see. I'm wondering if the question that I picked is the one that has a lot of data or not. If so, I probably won't put in all the data into the calculator, which would give me a different answer, but we'll see. Okay, so let's do this. Let's try another problem. And the problem that I've picked out is actually problem 15. So let's see, let's go in here. Well, we'll just hit this twice. It'll be easier. Oh, a sample of 50 cities with high and low temperatures. That means I'd have to put 100 data pieces into the calculator. Maybe we'll do a different example on the calculator. Let's see what we have here. 51 different regions. Yeah, that doesn't help at all. Okay, so let's do this. I'm not going to show you how to do it on the calculator. If you want to see it on the calculator, I can post it on my YouTube channel, but I'll do it with fewer data points because otherwise you're just going to see me put it in data for 10 minutes. Okay, so here's what we're just going to do this one with MyStatLab. Works really, really nicely. Okay, a random sample of 50 cities have the data on average high and low temperatures in January shown in the accompanying table. Use the technology of your choice and the given data to complete parts A through F. Use high temperature as the explanatory variable. So high temperature, they call it the explanatory variable. That's my independent variable. So we know that's the independent variable, high temperature, because that's my X. Y, which is low, that's going to be my dependent variable. Okay, so let me show you a couple of things. First of all, if we looked at A, you would not find a regression equation for this because it doesn't look like it's in the shape of a line. B looks linear. C looks linear, although it's flat. It'd be a horizontal line. And D is linear. We can see, oh, as the high temperature goes up, so does the low temperature. All right, so what we're going to do is we're going to look at these. We're going to figure out which one's the best. But the computer's going to do all the work for us. So we click here to get the data. It says, oh, there's the data. And look, it's just a huge amount of data. So what I'm going to do is I say, okay, that's nice. Let's open it in StatCrunch. And notice what they're trying to get us to do here. They just want a scatter plot of it. So here's what we do. We go graph, and we come down here to Scatterplot. Boy, that was hard. Click on that. It says, what's your X variable? Oh, they said that was the high temperature. So we say high. What's your Y variable? Oh, that's low. And the rest of these are just optional. We just say, you know what, compute it. Oh, look at the graph. It looks linear. It's going up from left to right. Well, let's see. Do I have any graphs that do that? Let's take this. Let's drop that down. Oh, it's going up from left to right. Oh, it's D. So we go and we click D, check our answer. And of course, right, the computer did it for us. That was not hard. Decide whether finding a regression line is reasonable. Yes, it's reasonable because the graph looked linear. It looked like a line would fairly well fit it. On A, we would have said no. We can't, we don't pick a linear equation for that. The computer will calculate one, even though it doesn't work very well. It works as best as it can. So you have to be careful. Don't ask it to do something that's not going to make any sense. So here we'd say, there's a clear curved pattern. No, there's a clear linear pattern. There's a clear curved pattern. No. There's a linear pattern to the data. Okay, so it's appropriate to carry out a linear regression. Well, that makes sense. Let's see. D says there's a linear pattern, so it's inappropriate. No, it's appropriate. And there's no clear pattern. No, it's C. There was a linear pattern. All right. Determine and interpret the regression equation. Now we have to actually find the regression equation. You know what? It's easy. Let's go back here. Let's go back. We'll pull this up. I don't need the graph anymore, so we'll close that down. But I need all the data. Watch this. Stat, regression, simple linear. So it's a line, so we pick linear, simple linear. What's the X variable? Oh, it's the high. What's the Y variable? Oh, it's the low. Now notice we can do hypothesis tests and confidence intervals. We'll look at that later, but not yet. Right now, I just say, oh, you know what? Go ahead and compute this for me. Compute. Okay, the intercept, remember that's my Y sub, oh, excuse me, that's my B sub 0. And my slope, that's my B sub 1. Oh, they put it up here for me. They say, oh, the low, which was Y, is negative 7.616, all that stuff plus that. So this is Y equals negative 7.6 plus 0.9x. And let's see how many decimals they want us to go. 3 decimals. So let's write this down so that I have it correctly. So to 3 decimals, I'm going to say Y equals negative 7.616x. Oops, there's no x there. Negative 7.616 plus 0.919x. Let's try that out. Let's drop all this down and let's try it out. So the regression equation is, which means there is a positive linear relationship. Now a positive linear relationship, that means the slope is positive. And we had the 0.919, which was a positive number, so it has a positive relationship. It means when x gets bigger, y gets bigger. It means you're going up from left to right. So it is the positive relationship. Negative would be a negative slope, which is what we don't have. And the line would be going down from left to right. So we do have this. So my y hat value, that's where I plug in, let's see. I need to find it. Oh, I need to make this bigger. Oh, that's not helping. Okay. Guess I have to use my keyboard again. All right, so let's flip that. Oh no, good heavens. I already had it flipped over, that's why I couldn't find it. All right, so I'm gonna put in, yeah, I'm ready. So my y hat was negative 7.616. And my x was 0.919x. Check my answer. Hey, we got that one too. Oh, that's all the parts. So that part's done. Oh no, there's parts remaining, I see. So we're not done. What else do we have? Let's see, so there was C. D says identify outliers and potential influential observations. Let's look back at our picture. I don't have anything that's far away from the rest of the data, so I don't have any outliers. and nothing would pull the regression equation away. We've got this one point, but if I put a line through here, it's pretty close to the line, so it's not going to do much at all. So I would venture on this one. There is no outliers and no influential observations. Let's see. Let's see if they're picking that one dot as an outlier. Let's check. They are not. So we were right the whole time. All right, so let's see. In case of potential outliers present, remove it and discuss the effect. So what you would have to do is you'd have to take that data point out if there was one and then redo the regression equation. We didn't have one, so we say there are no potential outliers. And then, oh, in case of a potential influential observation, remove it. There are no potential influential observations. Good job, next question. So we're done. So that was the idea. If we had a small data set, notice this one's gonna be very similar. If we click, there's 51 different regions. So that one, you definitely wouldn't wanna put all that data into your calculator. But we don't have to. We will just use, we would just go ahead and use our StatCrunch to do it. Notice here, let me give you a heads up. This dot right here, or this dot right here, or this dot right here is not close to the rest of the data. That would be a potential outlier, but it falls on the line, so it's not an influential observation. But if this is my graph, I would definitely say, hey, we do have a potential outlier because it's not near the rest of the data, but it's not changing my line. So it's not a potential influential observation. Okay, so anyway, that's the idea. Hopefully that helps you out. Again, if you want to see it on the calculator, just let me know. I'll post a video. I'll do one with a smaller data set and show you how to find the regression equation on the calculator. It's equally as easy. We just have to put in the data by hand ourselves. So that's the only thing that makes that a little more difficult. So anyway, that's it for today. Hopefully that helped you out. Luckily, just 2 sections today. We only have 2 sections a day for the remaining lectures. So that's always good. All right, so hopefully that helped. Get your homework done, ask insightful questions, and let's just finish the semester off strong. All right, you guys have a great day, and I will talk to you later.